You want to speak here or there? Okay, I'll speak here. We'll see. Redo? Okay. Bomo začeli. Lep pozdrav vsem v slovenščini. Zdaj pa bom preklopil na angleščino zaradi prenosa in upam, da boste imeli tudi vsi, da ne boste imeli težav z angleščino. So, good morning to everybody. We will start now with our second part of the Water2REturn presentation. Our program for this session is targeted more to general public, to farmers, perhaps wastewater operators, less to the slaughter industry or meat industry that was the focus of the first part of the presentation. And we will have 3 to 4 presentations. One is general introduction of the project. Then we will talk mainly about legislative aspects and the circular economy. Then a session on biostimulants and biofertilizers, and then conclusion and questions and answers. My name is Robert Reinhardt, coming from Algal, a Slovenian company working mostly with algae and algae-related technologies. We have a small booth at the very end of in this direction of the exhibition, and you can see an example pond there, and we also have some pictures, and it's a place for further discussions if anybody wants to see more or discuss more the algal, any part of the wastewater, of the Water2REturn technologies. Our colleagues here, mostly from Italy and from Belgium, will also be here today on the booth later after the presentation for some time. So my part of the presentation is general presentation of the project, the Water2REturn. We will discuss at length, slightly more than usual, about why is the reason or the reason behind the project. We will talk about the Water2REturn, the factual data in the nutshell. We will show the very general structure of the demo system that we have, and briefly address the potential clients and just show the consortium that did the project. So, why Water2REturn? Actually, it's a project focused on resource recovery, and I would like to go at some length in this story why resource recovery connected to wastewater is an important, socially important or technologically important topic that we need to address with technologies very similar or like Water2REturn. Water2REturn is focused to food industry, slaughterhouse industry actually, but the ideas behind that are more general. We could do the same or very similar things with municipal wastewater or with any kind of wastewater, but the products that we produce from this wastewater are focused for agricultural use. So, just a very brief global view. All nutrients that come, this is like the picture here represents the whole system, our life somehow. We see the input of nutrients in the far left side. So we have nitrogen produced from, actually captured from the atmosphere into ammonia. We have phosphorus mining, we have potassium mining, and this represents fertilizers that enter the agriculture, and then agriculture consumes all this, and this is actually the whole input of any nutrients into the system. then via crops or via some kind of waste, all industry and all consumers actually consume these nutrients in form of vegetables, crops, food, anything. And we are from this stage we are producing waste and wastewater. So all nitrogen, phosphorus, potassium that enters the system is released. I have to moderate my hand movements. Is released through these two streams. These two streams, wastewater and waste. With waste, we don't have much, well, this is not focus of our discussion, but in wastewater, all these nutrients come out, and of course, with wastewater treatment, like it's done today, we release all the organics into CO2, we released hopefully all the nitrogen to atmospheric nitrogen, and we released some of the nutrients into the environment water, and some of the nutrients remains in wastewater sludge. That's what it's mostly phosphorus, potassium. That's the status of what we are doing with wastewater, well, with water balance globally now. Let's focus for a second on the energy consumption in this picture. For the production of nutrients, we use huge amount of energy. This is the fossil fuel energy, mostly methane, natural gas, and you see the number, it's approximately 1.2% of total energy consumed by the humankind is used for fertilizer. This also produces quite a significant amount of greenhouse gases. So 1.6 to 3.8 tons per ton of ammonia, of release of CO2 of fossil origin. So this is the source of greenhouse gases. Then, of course, the energy is consumed by other systems. In this picture, of course, we use it daily. And then if we come to the end of this story, let's focus slightly on the wastewater. Wastewater has approximately 2 to 7 kilowatt hours of energy embodied in the organic contents of wastewater, talking about municipal wastewater. So now 2 to 7 kilowatt hours are there. If you would dry and burn it, that's the amount of energy that you would get out of that. And we are actually producing the total energy released in wastewater, well, released, let's say, flushed with wastewater, in Europe is approximately 1,500 terawatt hours. Compare this to the production of energy, it's quite a significant amount. So, and in the treatment of wastewater, we actually consume approximately 1% of total electrical energy. So in the water system consumes approximately 2 to 3%, depends on the economy, of all electrical energy. Just notice this is electrical and this is total energy. So, and 1% is used in the wastewater treatment. Approximately 70% of that is used in just blowing air to the water, so that bacteria are able to consume the organic matter in the wastewater. And of course, today in the world, approximately 40 to 80%, depends on how you count, of water is untreated, is released to the environment untreated. So these figures will just rise when the developing world will do their wastewater treatment in, so the balance, it's slightly, I mean, it's a significant issue worldwide. So we have to do, I mean, it's not as significant as traffic, for example, but it's a significant issue. So since we are talking about large amounts of energy and materials. So, what we can do to recycle to recycle at least the energy and some of the nutrients, we actually add an anaerobic digestion stage here. So waste and wastewater sludge can be treated by bacteria to produce biogas, which will recover some part of the energy from these streams. And that is done at many wastewater treatment installations, but only the large ones, where the cost of these approaches is comparable to the cost of the treatment. And then, of course, we produce some of the digestate that goes to fertilizers back, and that's partial nutrient recovery, and this, the energy produced in this area is partial energy recovery. So let's recap the story. 2 to 7 kilowatt hours per cubic meter of wastewater is flushed to the system. We consume approximately 0.5 to 2 kilowatt hours additional to that to treat this wastewater. We still release a significant proportion of the nutrients to the environment. The contents of most of the organics in the wastewater is converted to CO2. So it's not reused, or not anything is not done. The idea of wastewater operators is to release as much of the organic material in wastewater as possible into the air, as CO2, of course. And their idea is also to release as much of nitrogen content embodied in organic nitrogen or ammonia or nitrates into gaseous nitrogen into the atmosphere. With each ton of non-recycled nitrogen, we have released, let's say, 3 tons of CO2 to produce it. So when we release it to the air, we just lost this energy. And some other very potent greenhouse gases are produced in the process. So all these calls for better nutrient and energy recycling technologies. Water2REturn is one of those projects focused on doing just that. So recycle nutrients, recycle energy, and produce something useful. And this is the nutrient, what we want to do in our schematics is to add some algae here to better recycle nutrients, to reduce the amount of energy for aeration, then consume the algae in anaerobic digestion, and of course reduce the energy consumption in wastewater treatment. Of course, with that, we increase the amount of digestate that we have, but this also provides the loop back to the fertilizer box. What is possible and proven in some installations is that all these can be made energy positive. So instead of using 0.5 kilowatt hour for treatment, we can extract most of the energy from the wastewater to consume in the process again. What is quite important to say here that all this is done very distributed. So you have many wastewater treatment plants, and to do anything significantly in this area, we need to have a very distributed solution. We need to have logistic chains adapted, we need to have energy production adapted, and many things more, which make this approach, let's say, at least non-trivial. It's not simple to implement it. It's not simple to say we will recycle most of the nutrients or we will recycle most of the energy. In isolated cases, like in this particular case, slaughterhouse, it's possible to do, and that was the aim of the project to show. So, come on. Water2REturn. The idea is to recycle all the nutrients from the slaughterhouse waste and to recycle some of the energy and produce agricultural products, fertilizers, so nutrients come into fertilizers, biostimulants in the form of bacillus strains grown on wastewater sludge, and algae in the algal biostimulants in the form of algae biomass produced on liquid flows from the system. In a nutshell, okay, just the formal things. It's a Horizon project. Like most of the Horizon projects, it used to be 3 years old. Now it's the duration is 57 months after extension for COVID and so on. You have the general data on the project here. We have a demo site in Spain next to Matadero del Sur slaughterhouse, where the climatic conditions for our project are quite favorable, at least for the algal part. And this demo site is operational now, producing what we have promised. The system, okay, this is the schematics of the system, but I prefer to show it in this way. So we have, in principle, 3 parts. The top part is water line, a classical water line treating wastewater in a conventional aerobic way. But then with the addition of the last stages, which are micro, ultra filtration and reverse osmosis, which also extract remaining nutrients from the water stream. The sludge, and you know the sludge from the wastewater treatment is quite a problem. The sludge is dewatered, used for bacillus growth, and this is producing biostimulants, Bacillus subtilis or similar strain. The process water that comes from these systems goes into an anaerobic digestion where we do energy recovery, and then the digestate from this energy recovery and some other streams are brought into the algae pond where we are growing algae biomass that is transformed into the biostimulants. That is all operational. This is done by different partners, different parts, and that's it. This is just written again, the products that we produce. And the idea is to, instead of pay for the treatment of wastewater, to get those market value of those products back to cover the wastewater story of the slaughterhouse. I think I mentioned the key innovations and results. We have economic products, we have secondary raw materials. The location of the demo system is next to Seville, as I said, in the second most hottest city in Europe. Treatment capacity is slightly more than 50 cubic meters per day for the water, and we are actually producing, this is some pictures of the system, the water line, the Bacillus subtilis fermentation, the energy recovery, and the algal system in front of, this is another picture. Some of the results, well, of course, advantages and challenges. Advantages are clear. Anything that makes water treatment for free is welcome by industry, even more if it makes some revenue from that. Challenges are, of course, legal framework. We have an issue with products produced from waste. So there is a general end of waste directive in Europe, which is implemented in different ways in different countries, and we have quite an activity at European level to harmonize this, to make some of the products less complicated to be approved for reuse and so on. Then, of course, a very common challenge is complexity of the system. I mean, the system is, like, I would say, 3 to 5 times more complex than an ordinary wastewater treatment system in the slaughterhouse. This complexity has to be justified with the revenues produced from the products. Clients, well, in general, I presented the system very general. So clients are come from anywhere, but for this particular system with this particular setup and this particular experience, of course, is targeted for any food industry, slaughterhouses, of course, more general food industry where even some of the waste streams could be seen as side streams, not waste. I mean, whenever you have a stream that is now something like a waste stream, but it's actually very controlled origin and very controlled composition, this can be declared as a side stream. For example, cleaning water from milk industry is one such example. We can grow algae for food on cleaning water of milk industry if, of course, this is declared as a side stream from milk industry, not a waste stream. But in general, in this particular project, we are focused to agricultural sector. And just final words, the consortium consists of 15 partners from, I think, 8 countries. And you see logos of all of those. It's a very balanced consortium, and some of the partners, well, we have quite specialized partners doing parts of the system in a very independent way. I think that's the general introduction. I think we should show the video now. It's already open if you just start it. Just press.
In light of climate change, land limitation, and soil degradation, there is rising demand for alternative and sustainable solutions to maximize water use efficiency and to recover resources from going to waste. However, the European food industry, especially the slaughtering sector, has a high water and energy consumption, producing significantly large amounts of wastewater containing nutrients that end up being discarded. This results in serious environmental risks. So what if we reverse this process and turn wastewater treatment facilities into nutrients biorefineries? The Horizon 2020 project, Water2REturn, provides a cutting-edge solution for slaughterhouse wastewater treatment while recovering resources. It adopts a circular economy approach. The project's demonstrator is being run at the Matadero del Sur slaughterhouse premises in Solteras, a region well versed in water scarcity challenges. This integrated system not only treats wastewater, resources to be further turned into high market value products for the agrochemical industry. Concretely, for each of its treatment lines, the system recovers 3 different secondary raw materials: nitrogen concentrate, hydrolyzed sludge, and algal biomass. These form the basis to further manufacture agronomic products, 1 biofertilizer and 2 biostimulants, ready to be used by the agricultural sector. This way, the Water2REturn approach not only contributes to reduce the production of chemical fertilizers that may cause environmental problems, but also solves wastewater management issues in slaughterhouses, while reducing water and energy costs at the same time. Water2REturn's innovative resource-oriented solution for industrial wastewater treatment is transposable to the needs of diverse industries and end users, as well as responding to a rising demand for sustainable alternatives, increasing water usage efficiency and resource recovery, making it an optimal framework across Europe.
Now with this, I pass the podium to Daniel. You will introduce yourself and continue, right?
It's in Slovenian, so I can't. Sorry? How do I set up the PowerPoint or the?
Just press this one. Yeah.
Good afternoon. My name is Daniel Monteleone. My name is Daniel Monteleone from the European Landowners Organization. I'll give you my presentation on. There we go. Coming from ELO, European Landowners Organization. It's the largest landowners organization representing group in Europe. In Brussels, Belgium is where we're based. My speech will be on three different parts: the regulatory aspects of biofertilizers, the importance of organic fertilizers, and the environmental benefits, of course, of Water2REturn products. So here's a list of different regulatory aspects that are associated with the project Water2REturn. INMAP, which we'll go into that later, the EU Fertilization Regulation of 2018 and 19, national policies, Water Framework Directive, Sewer Sludge Directive, Farm to Fork Strategy, and the EU Biodiversity Strategy for 2030. But since we're mainly addressing fertilizers, we're only going to go at the first part of this list. INMAP, what is it? It's the Integrated Nutrition Management Action Plan. It's currently being developed at the European Union. The Commission will develop an integrated nutrient management plan with a view to ensuring more sustainable application of nutrients and stimulating the markets for recovered nutrients. The Commission will also consider reviewing directives on wastewater treatment and sewer sludge and will assess natural means of nutrient removal such as algae. This plan is being developed in connection with Water2REturn by the Commission. Of course, Water2REturn is a project that deals with wastewater treatment and sludge and assesses means of nutrient removal, including algae, which is why this policy is so important, and it'll be coming into effect in the next year. We presented this project, Water2REturn, to the European Commission this March. We advocated for a standardization of regulations across the EU instead of having 27 different regulations. And we try to advocate giving incentives to farmers for using biofertilizers, which we call the carrot, rather than punishing farmers for not using them, which is referred to as the stick. And that's an image from our slide. What about the EU Fertilizer Regulation 2018 and 19? It goes into effect in July 16th of next year. There's a lot of different aspects, but there are a few changes from the previous one in 2003. It will be opening the single market for bio-based fertilizers. The agreement on the fertilizing products regulation will open the market for new and innovative organic fertilizers, such as, of course, Water2REturn. There's going to be rules on safety and quality. The new regulation will provide strict rules on safety, quality, and labeling requirements for all fertilizers to be traded freely across the EU. This is something that we're also taking into account on this project, as we're ensuring that the products we create are safe and within these regulations as they're being developed. The EU fertilizers products will be divided into different product function categories, which should each be subject to specific safety and quality requirements adapted to their intended uses. Component materials for EU fertilizing products should be possible on the market. An EU fertilizing product composed of several component materials from various component material categories, where each material complies with the requirements of the category to which the material belongs. And finally, it'll be introducing new limit values for contaminants in fertilizers. Once again, all these things are being taken into account with the Water2REturn project, and we ensure that we don't have the contaminants that are opposed, and we have a nice clean material. We'll also just briefly address the other stuff. Farm to fork strategy. It calls for a reduction of nutrient losses by at least 50% while ensuring there's no deterioration in soil fertility. This will reduce the use of fertilizers by at least 20% by 2030. This is also the same document, Farm to Fork, where the INMAP was proposed. That's the one we addressed earlier. National policies, nearly every member state has their own rules and regulations on biofertilizers. When the original legislations were written, fertilizer policies, around the year 2000, they were innovative. But now, most member states have surpassed the EU policy. However, with 27 different countries, it becomes difficult to determine what sort of biofertilizers to invest in on your farm when national laws can change at any time. Now, second part of our presentation is organic fertilizers. What are they? Many of you know, but we'll still explain it. Organic fertilizers are substances that are derived from the remains or byproducts of organisms. They are rich in phosphorus, nitrogen, and potassium, but often in unequal proportions. Examples of organic fertilizers are cottonseed meal, blood meal, fish emulsion, manure, sewer sludge. There's two types of organic fertilizers. First is the synthetic type, which is an organic compound produced artificially, for example, urea. And the others are natural fertilizers because 100% of the ingredients used to create a typical natural fertilizer come from nature. For example, fish extract, seaweed, manure, guano, and compost materials. In comparison, what is an inorganic fertilizer? A chemical fertilizer is defined as any inorganic material of wholly or partially synthetic origin that is added to the soil to sustain plant growth. Chemical fertilizers are produced synthetically from inorganic materials. Some examples: ammonium sulfate, ammonium phosphate, ammonium nitrate, urea, ammonium chloride, and the like. Why are organic fertilizers so important? Well, for example, they improve soil quality. They help microbes thrive. They help avoid plant damage, whereas synthetic fertilizers can often cause plant damage to leaves and roots. They're sustainable and environmental friendly. According to the Organic Trade Association, organic fertilizers also increase species biodiversity by 30% compared to synthetic fertilizer. Finally, they reduce fertilizer and pesticide use. Although they can be more costly sometimes, they can also reduce the need for pesticides and the overall nitrogen, phosphorus, and potassium requirements. Because of the reductions, organic fertilizer can be cost neutral and sometimes even a cost savings. To be fair, we will briefly address the negatives of organic fertilizers. Not all products are created equal. Make sure you're selecting product that is industry vetted by reviewing any university studies or case studies or products that come from a project that's been worked on by many partners with many backgrounds at universities and many case studies. And sometimes nutrient levels are low. The level of nutrients present in organic fertilizer is often low, but of course, that's something that we fix with Water2REturn. What are the environmental benefits? Wastewater treatment and raw material extract for slaughterhouse are two of them, but those were also briefly addressed in the other presentation. And most people here are farmers, so we'll discuss the third part, the agronomic products. 3 agronomic products manufactured in production lines built up within the Water2REturn project will be free of pathogens and pollutants and ready to be commercialized. 1 organic fertilizer and 2 biostimulants that will enhance nutrition, efficiency, abiotic stress tolerance, and or crop quality traits. This is also what you saw in the previous video. The different parts of it. Secondary raw material 1, 2, and 3. The first part is soluble nitrogen and phosphorus. This is an organic fertilizer with the nitrate and phosphate concentrate. Second part is the hydrolyzed sludge, which is a biostimulant product to enhance nutrition efficiency, abiotic stress tolerance, and or crop quality traits. Finally, the third part, algal biomass, a biostimulant algal based product. Another environmental most important part. These products are free of pathogens, free of heavy metals, and free of emerging pollutants, allowing for the safe reuse of slaughterhouse water, fully valorized thanks to this cascading process, and thus safe for use in both the EU and internationally. Other parts, of course, reasonably priced. For the slaughterhouses, the process pays off for the slaughterhouses using the production within 2.5 years, thus inexpensive. It adds more fertilizer and bioproducts to the market and will make up 4% of the entire organic fertilizer market, thus decreasing the other fertilizer prices that's due to supply and demand. Finally, it fulfills the increasingly restrictive legislation on agronomic product manufacturing and use. Thus, it remains in line with all existing legislation. And you already saw the video, so I hope you liked it. I will be here after this presentations if you'd like to discuss it. The audience here was the first to see it, so we want to have your thoughts on it. So let me know your thoughts after this session. And if you have any questions, let me know. Otherwise, talk one-on-one after the presentations are completed. Thank you.
Okay, now the next presenter will be Professor Rok Mihelic from University of Ljubljana. They did most of the biostimulant testing of within the Water2REturn project. So, Rok, please. Floor is yours.
Okay, thank you very much also from my side to be here. I will talk today about biostimulants from algae and the market potential. This is what we are doing in University in Ljubljana together with partners of Algal. You have seen all the schemes of the project, so I will not repeat everything. And I will concentrate to the results of the algae line. Here you see the installation in Seville in this project site. So in front of us it's a large algae pool from where this is a final step of the treatment of slaughterhouse wastewater. And we are also doing experiments in Ljubljana in greenhouse where we have these smaller experimental pools. Some words about biostimulants. These are not fertilizers. So we are not it's not the aim to put nutrients in soil or to the plant by the biostimulant. That's our fertilizers for. And the biostimulants are the substances which can promote regular and alter physiological process in the plants to promote growth, alleviate stress, or and the end increase yields. They are complex compounds that include bacteria, fungi, seaweed, also some parts of higher plants, animals, and there's a great variety of industrial processes to prepare biostimulants. And there are also several definitions of the biostimulants, but one which is quite new is that it is a formulated product of biological origin that improves plant productivity as a consequence of a novel or emergent properties of the complex of constituents and not as a sole consequence of the presence of a known essential plant nutrient, plant regulator, or plant protective compound. So it's a complex of various substances which can promote the health and the life of an individual plant. But of course, when we are talking about the complex of substances, we still need to prove the efficiency and the safety of those, and we need to determine the action of the mechanism of the action, and of course, again, we do not need to prove a specific compound to be active. We just need to see the repetitive and the known effect of these products. There are many definitions, and there was the development of those. The first who was working with biostimulants was maybe Filato in the end after the Second World War. The important is that we know that the substances are working in low doses. You will see later on it's enough that we put 1 kilograms to few kilograms per hectare to work on plants, or when we apply it by a foliar application, it's 1 to 10 grams per liter. It's already working. And it has to be stressed again, it cannot replace fertilizers. We do fertilize the crops normally. We use biostimulants only to improve some stages of the growth, for example, the time of germination and early root development, or in the time of starting flowering the plant, or maybe to improve the fruit quality. We intervene with biostimulants often also in the stress condition to improve maybe water intake and to improve the intake of nutrients. Biostimulants are also not pesticides, so it's a special group. At first, they discovered that humic substances extracted from some fossil plant material were effective as biostimulants, and in the last years we see that the seaweed, so macroalgae from sea, are very effective. But new research we are now conducting on microalgae. Microorganisms in the water can produce the same substances as the algae from the sea. And this microalgae can be grown in controlled conditions, and that's the advantage according to the wild plant species we gather. So microorganisms, including microalgae, are now in focus of the research of new biostimulants. So the key mechanisms are raw scavenging. It means that biostimulants alleviate the oxidative stress. They improve the membrane stability, they protect the plant against osmotic stress, they regulate the opening of stomata, and so on. So many effects, many of them like hormonal effects. So they help plant with rooting, develop strong root system, improve growth of the shoots and roots, increase fresh weight of grains and crop components, increase the number of fruits per plants, yield, size, and quality. All of this is very important with maybe vegetable production, which are really it is important that the producer is of high quality and that the product hits the market very early, before the competition, in front of competition. Yes, and the typical application rates are really small. This is maybe surprising for somebody. That's 3 to 10 grams of the preparation per liter for foliar application is enough, but we have to apply it 2 to 5 times per growing season. Or for example, just 0.3 grams per liter to put onion bulbs before we put the onion to the soil. Or we can soak the plant seeds by 0.7 grams per liter, for example, for 18 to 24 hours before putting the seeds to the soil, and this is proven to improve the growth of the plant. And when we apply it to the soil, 1 to 4 kilograms per hectare of dry matter of microalgae, for example, improves the growth of the plants and improves also the rhizosphere composition. It improves also the life of soil microorganisms. The market, there is an expected fast growth annually by 12%, and the whole market of all biostimulants is expected to reach $5.5 billion by 2027. Now, at the moment, the share of microalgae is negligible. So it's really the starting of expansion of this global market, and that's why it's very interesting to be here at the beginning, at the start of the market development. The market price of microalgae for biostimulant is around 10 to 80 euros per kilogram on a market. So it's also, this is quite tempting for producers. And the cost for farmer per hectare is around 100 to 600 euros. So again, the production of these biostimulants fit nicely into the scheme of circular economy. And of course, it can be produced also directly using like hydroponics, but it's very sensible that we use the nutrients from other cycles, that we use photosynthetic active microalgae to take out the nutrients and to produce valuable substances. We have some experiments and some practical experiences in our algae park. In the wastewater stream, strain Senedesmus is very effective, and there are some filamentous cyanobacteria also growing there, but Senedesmus is the most prevailing substance. And in liquid digestate, we were able to produce in the circumstances without artificial light in the central Slovenia, in Ljubljana. The production is 7 grams of algae dry matter per square meter per day. It's not very high production, but is fine that we get from a substance which is really low value, so some food digestate, we get some valuable product. And this can be used as you will see, as a biostimulant, but the water from growing algae is very useful for further growing vegetables as hydroponics. We are testing the material, the algae produced as they are so non-treated and with some pre-treatment process. And sometimes pre-treatment is successful, sometimes it is not necessary. But we quite often get longer roots compared to the control, for example, compared to water. This is, we can see this effect almost in every occasion with different plants and different extraction systems produce, for example, 60% longer roots or a more developed root system when applying algae. Yeah, also we are testing this in some agricultural crops. So to conclude, cultivation of biostimulants should be focused to the highest algal biomass production without culture collapse of. So it's really important that we are focusing on the specific needs of the algae which is grown. So algae is not just is not the organism just to take the nutrients from the stream, but we have to take care for the algae if we want to have a good effect of algae for biostimulants. Stenodesmus is a very good strain to grow on digestate. It can be successfully inoculated from Slovenia also to the Spain. And we found out that Stenodesmus had auxin-like activity. It affects the plants which are visibly bigger and with bigger and stronger roots. We can make the effects higher when we extract the algal culture with high pressure homogenization or enzymatic treatment, but it's not necessary always. Also, the non-treated algae works quite well. And after we extract the biostimulants, the water which stays is very good source for growing hydroponically vegetables in greenhouse as well. So thank you very much. This is the team from Algin we are working with. Yeah, and further questions are welcome. Thank you.
Daniel, you have final word? So, but if there are any questions, we are open for questions anytime, so go ahead.
The last part was just to let you know that we have questionnaires if anyone would like to fill them out. We have people in the audience who will help set you up with that. And once again, if you have any questions about the video or anything you'd like to say about it, you can meet with us at those tables in the next 5-10 minutes. We'll be there. And I think that's about it. So, thank you.